Welcome, guys, to the second part of the Chapter 4 lecture, talking about calculating different things as well as balancing equations. Here we're going to look at, in more specifics, what a limiting reagent is, what a theoretical yield is, and what the actual yield is. And so what we're going to do is let's go ahead and we're going to look at the example that the book uses just because I really like it. I really like pizza. And so what we're going to do is we're going to look at this in terms of pizza. And then what we're going to do is we're going to look at just a few different problems that we can use a balanced equation to calculate. So let's look at this. So stoichiometry, right, allows us to calculate, we said, limiting reagents or reactants. We can use reactant because it kind of reminds us on where in the equation they fall. Theoretical yield, right, is what's the maximum amount of product that we can make from our limiting reagent. And then the actual yield, right? What if we went into the lab and we actually did the experiment and we measured our products? What is the maximum, or what is the one we actually get? And what we can then do is calculate a percent yield, right? That how close were we to the theoretical value? Now, let's look at pizza, because I like pizza. I don't know many people who don't like pizza. But what we're going to do is we're going to use and your book uses this example. I like this example because it's really straightforward to what a limiting reagent is. So let's say in our pizza, right, that it takes one crust to make one pizza. It takes 2 cups of cheese on one pizza, and it takes 5 ounces of tomato sauce per pizza. So, and right now we have our list of ingredients on there. We see the crust, the cheese, and the tomato sauce. So it takes 1 crust to make 1 pizza. So let's say we have 4 crusts, right? Well, that obviously will make 4 pizzas. We said it takes 2 cups of cheese to make 1 pizza. And here we have 10 cups of cheese. So we're going to make 5 pizzas. And then let's say we have 15 ounces of tomato sauce, and it takes 5 ounces per pizza. So we take 15 divided by 5. And we're going to get 3 pizzas. Now let's look at the products formed to determine which one is the limiting reagent. And we're going to do this exactly the same in our calculations with our balanced equations. And so let's look. So with the crust, we had 4. With the cheese, we had 5. And with the tomato sauce, we had 3. Well, obviously 3 is less than 4 and 5. So that is the lowest amount of product, which would then make the tomato sauce our limiting reactant, and then the 3 pizzas that the limiting reactant makes would be the theoretical yield, right? Because you can't make any more than 3 pizzas from that tomato sauce. Now, let's say you go into the restaurant and, some stuff gets lost, right? Because they're flipping around the crust or they're doing some other stuff, and you only make 2 pizzas. So with 15 ounces of tomato sauce, you only make 2 pizzas instead of the 3 that you could theoretically make. The actual yield would be 2, right? The theoretical yield was 3. So then the percent yield would be 2 divided by 3, right? Actual divided by theoretical. And so we know that 2 divided by 3 is 0.66. So it'd be about 66%, right? Now, it's a lot of words. Let's go to the board. And so we're going to actually start to calculate limiting reactants, theoretical yield, and percent yield. So let's go ahead and go back. And I have my calculator. So let's go ahead and go back to the previous example that we talked about with in part number 1 with photosynthesis, right? Where we have CO2 plus H2O with the energy derived from the sun, leading us to make oxygen gas as well as glucose. And what we're going to do, let's put this down here. What we're going to do is we're going to calculate. So I'm going to show you how do we calculate how much product is made from a reactant, right? We're going to show you this step first. And what we're going to see is that these steps are all very, very, very similar. And so what we're going to do, right, is we're going to start with what we know, right? What do we know? That we have 37.8 grams of CO2. Now, what do we want to end with, right? Because this is what we talked about with the problem solving, is we want to know what we start with and we want to know what we're going to end with. And that's right, we're going to try to find grams of glucose. So how do you think we go from grams of CO2 to grams of glucose? Well, we don't have a direct connection to where we go from grams here to grams here. But we do have an intermediate. And that intermediate is moles. And so what we can do is look at the molecular weight of CO2. The molecular weight of CO2 is 44.01 grams per 1 mole of CO2. So right now, if I were to just divide this by this, we would have moles of CO2. So if you need to break it up, you can. If you want to just continue it on like I will, you can do that as well. Again, whatever's easier for you. Okay. So let's look at our balanced equation, right? Because we said we have a molar ratio. So now can I convert moles of CO2 into moles of glucose? Yes, I can do that because that's what the equation tells me. This is what the equation tells me. And so for every 6 moles of CO2, I can produce 1 mole. I'm going to run out of room in my box, of glucose, right? So now, if I were to just calculate it from here, what would I end up with? You're right, moles of glucose. So let's say, but is that what I want to solve? This is where knowing what we want at the end will help us determine how to get there, right? And so I want moles or grams of glucose. So we have to do one more step, right? Again, going from moles, right? Going from moles to grams, we're going to multiply by the molecular weight, which is 180.2 grams. So now let's just make sure, and I'll do this in green. So maybe we can change the color. So let's make sure that what we're actually solving for is what we're gonna get. So the grams of CO2 cancel, the moles of CO2 cancel, and the moles of glucose cancel, leaving us with grams of glucose. And so remember, numbers on the top get divided by numbers on the bottom. Numbers on the top next to each other get multiplied. So what you could do is take 37.8 times 180.2 divided by 44 divided by 6, or you can multiply these two, multiply those two, divide them together. You can solve it however you want. Usually what I'll do is I'll do 37.8 divided by 44.01 divided by 6 multiplied by 180.2, just so I can go step by step by step. And what we end up getting is 25.8 grams of glucose. Right? And we have 3 significant figures here and 3 here, so our answer is fine. Now, this is the steps that we are going to be taking for a lot of these problems, where we're looking at grams, right? Where we're looking at limiting reagents, where we're looking at theoretical yields, right? And this is going just from one reactant to a product. So let's look at another example. So we have sodium phosphate. We're going to react it with barium nitrate, and we're going to get barium phosphate. Oh yeah. plus, let's move my board over a little bit, sodium nitrate. So what I would like you to do is I would like you to look at the equation, right? And so let's go ahead and let's look at this. I apologize, my board is moving around a little bit. This is what happens when you don't have an easel or it's not attached to the wall and you have to put it on your couch in your office. And so let's go ahead. And so what I'm going to tell you is this. We have 3.50 grams of this, and we react it with 6.40 grams of this. And so what I want you guys to do there we go. Sorry, my phone was ringing. And so what I want you guys to do is tell me how many grams of barium phosphate is made. Now, when we talk about these limiting reagent theoretical yield problems, you have to know what we're looking for with products, right? Now, on an exam or on a question in your book, if they say, hey, what is the limiting reactant in this reaction, and they don't give you a product to choose, just pick one. I'll show you the kind of tip on how to make the math a little bit easier. But otherwise, I am telling you that I want to know how many grams of barium phosphate will be produced. So that's the product that we're going to look at. Now, let's look at the first step in this equation, right? So let's think here. So we're given 2 grams. Oh, I know if you're not yelling at the screen, I'll have you look at this equation again, and then you'll start yelling. Dr. Bishop, you have to balance the equation first. Absolutely. You guys are right. I did that on purpose, right? Is that so let's go ahead and balance this equation. I want you guys to pause the video here. I want you to try to balance the equation, and then I will show you a little tip on how to maybe make an equation like this a little bit easier to balance. So go ahead and pause it, and I'll have you try to balance it, and then I will show you how I would balance it. All right, so hopefully you guys were able to balance it, or at least make a good attempt to balance it. So let's go ahead and look at this. I'm going to do something just real quick. These aren't in parentheses. This phosphate and this nitrate are not in parentheses, but I am going to put them in parentheses. Now, if you remember, you guys are supposed to memorize the polyatomic ions in table 3.4. Phosphate and nitrate are those polyatomic ions. When we try to balance this equation, I want us to think about these things being together, right? So instead of separating the phosphate out from the oxygen, keep the PO4 together. And we're going to balance those as a unit. So let's go ahead and start balancing these. I'm going to start with this phosphate, right? I'm not going to make the table because one, I already have how they're balanced on my paper, but I'm just going to walk you guys through just how to do it without the table. Now, I would recommend, until you get super comfortable with doing this just by sight, that you use the table, right? Because the table, again, just helps us clear our minds and helps us focus on the actual numbers of this. So I'm going to start with a phosphate. So we have 2 phosphates over here. We have 1 phosphate over here. So to balance that, we need to put a 2 out in front of there. Okay? So if we have a 2 in front of here, we now have 6 sodiums, right? Because 2 times the 3 here is 6. And so now we have 6 sodium, whereas we only have 1 over here. So I'm going to put a 6 right there. If we have 6 sodium here, or if we have 6 here, we now have 6 nitrates. We have 2 nitrates over here. And so what we need to do is 3 times 2 is 6, which matches this. we now have 3 barium. We have 3 barium here, and we are now balanced. Now, do you guys know what we do with a dead chemist? That's exactly right. We bury him. Just a little humor to break up some of the math that we're about to do. So the next thing I would do, so great. So we balanced the equation. Perfect. We know we're supposed to find this, the barium phosphate. How many grams of that are produced? And we're given grams of the reactants. So if you're given grams of a reactants and asked to find a product, or it just blatantly tells you, find the limiting reagent, we know this is a limiting reagent problem. Our flashers in our mind should go off. And so we know how to solve this problem already. We did it, or at least we know what pathway to take because we did it with the oh wow, my mind just drew a blank. With a plant example, turning CO2 into sugar. Wow, I am photosynthesis. Ooh, there we go. Photosynthesis. I was getting worried there. So, right. So we know that's this type of reaction. So we're going to go to grams to moles, and then from moles to grams. Now, your book. So let's go ahead and let's just go ahead and solve it. So the next thing I would do, just upfront work, right? Again, so the more work that we do up front, the easier just putting numbers in and doing the calculations will be, is to find the molecular weights. So sodium phosphate, the molecular weight is going to be 164 grams per mole. Barium nitrate is going to be 261 grams per mole. And then barium phosphate, right? This is what we're looking for, is going to be 602 grams per mole, right? So we're working with some really heavy molecules here because we're looking at some heavy metals like barium and phosphate's pretty heavy. So we have now our molecular weights. So let's think about how to solve this problem, right? Let's think about how to solve this problem. What I'm going to do, just so that we can get a little bit more bored. There we go. All right, so what we're going to do now is we're going to turn, because we want to find grams of this. So let's go ahead and set up this equation, or the math, like we did before. So we have 3.50 grams of, I'm just going to put Na3 just as a shorthand, just to save time writing. And we know 164 grams of Na3 is equal to 1 mole of it. So now we have a balanced equation. So again, what's the next step, right? Because we can turn now moles of this into moles of our product. So we know for every 2 moles of Na3, it's going to equal 1 mole of Ba3. Now, here's where, again, you guys can do whatever you want, okay? We have to do this. Let's go ahead and set up the other one. So we know we have 6.40 grams of Ba, and we know we have 261 grams of Ba per 1 mole of Ba, and we know for every 3 moles, we're going to make 1 mole of Ba3. Right? So if you were to do it the way your book describes, which is perfectly valid, you will do these calculations and you will find out the number of moles of product produced. The lowest number of moles produced will be your limiting reagent, right? Whatever gives you the lowest number of moles will be your limiting reagent. What I would do, just because it's me and we're punching numbers in a calculator, it's really not that much work, is I would just go ahead and do the one extra step, right? Because you still have to do this step, determining which one you find out as your limiting reagent, is for every 1 mole of Ba3, right, is going to be 602 grams. right? Because what we're doing, and you can't see the bottom, I apologize. So this is 1 mole of the product, and this is the molecular weight of the product, which would be 602 grams. And so what we're going to be doing is just converting both of those into grams of product. And I'll show you why. So this one is 6.42 grams of product. I'm just going to put a P for product. And this one is 4.92 grams per product. Now, what I want you guys to tell me, 4.92, it's on the edge of the screen. I think you guys can see it. So what I want you guys to do is tell me which one is the limiting reagent. So we have 6.42 grams of product coming from the sodium phosphate, and we have 4.92 grams of product coming from the barium nitrate. Exactly. This is your limiting reagent, or limiting reactant. Why? Because it produces the smallest amount of product, right? 4.92 grams per product. Now, the reason why I did this extra step here that your book doesn't do, but I did it right here, is because now we have the theoretical yield, right? We don't have to worry about, oh, I forgot to convert the moles of the product into grams because we already did it, right? And so now we know the theoretical yield is 4.92 grams of product. We know the limiting reactant is the barium nitrate. Now let's say you go into the lab. You go into the lab and you actually find out that you produce, let's see here. Well, can't find it on my notes. 3.69 grams of product, right? So we produce in the lab 3.69 grams of product. So this is the actual yield. Now, on an exam or on a test or on a quiz or anything, if I ask you to calculate the percent yield, right? The percent yield, and I do not give you the actual yield, you cannot solve that problem. And if you want to make a note like Dr. Bishop, you didn't give us this, I can't solve this, perfectly fine. Please do, because you can't, it's impossible. So we have 3.69 grams of product. We're going to divide it by 4.92 grams for the theoretical yield, right? Because remember, it's actual yield divided by theoretical yield, right? What we get from the lab divided by what we calculate of what we can get. And what we're going to do, wow, I did not. Let's go ahead and calculate this. For some reason, I don't have it in my notes, the actual answer. Right? And so this is going to equal 0.75. Since it is a percent yield, we'll multiply it by 100%, and what we get is 75% yield. That's actually a really, really, really good yield in the lab. And so what we're going to see, so a couple things to talk about. I'll switch to the other screen just so that we can look at a blank slide. Just a couple things to note. The step-by-step way that we solve, these theoretical yield problems are the same, right? Grams to moles of reactant, moles of reactant to moles of product, using the molar ratio from a balanced chemical equation, and then the moles of product to grams of product to find the theoretical yield. It's going to be, it's almost like it's very repetitive. And I think with the practice, we can get it. Now, in your book, and there might be other problems where you're given moles of reactant and they want you to find the theoretical yield. If you start out with moles, you're cutting out the first step of going grams to moles, and then your product can be in moles, right? Because if they give you moles, the product will probably be in moles too. And so just there's different ways to get on this track. And so we just have to be just constantly working on trying to do that. And so hopefully part two, we went through one quite large problem relatively slow. We went through a couple problems relatively slowly. And so we have practice problems for you guys to do. If you have any questions, again, while you're doing these problems, like Dr. Bishop, I just don't see it yet. Please let me know, and we'll work on getting you guys more practice and just trying to walk through some of these calculations.